You've seen almost all of the shapes, and there's one left, and that's the path shape. The path shape can contain any shape, group of shapes, or complex items like curves. What you need to do is supply the path.data property, or just the data property if it was just a single item, but because you'll almost always specify a complex value inside this property, you generally use the element.property syntax to specify it. And the path.data property contains a geometry object or some sort of collection of geometry objects. Now the geometry class is abstract, so you have to use either ellipse geometry, line geometry, rectangle geometry, or a path geometry which can contain arcs, curves, and lines. You can also place a geometry group inside the path.data property and group a bunch of geometries together. Geometry group acts as a container for other geometry classes. Now you're wondering, why would I use paths versus geometry? Why do both classes exist? Well, a geometry defines a single shape. A path can group shapes together and allows you to draw the shape or shapes. The path class also provides the stroke and fill properties, and it also handles the mouse and the keyboard. So think of the mouse as the overall container for shapes, and you can draw individual shapes using geometries inside of that path. We'll start with the same three shapes we started with before. We'll look at the ellipse geometry, line geometry, and rectangle geometry classes first. And these obviously work much like the ellipse, line, and rectangle shapes. You'll find the properties you set are slightly different for these, however. The ellipse geometry, for example, defines center and radius rather than width and height. The real power comes in combining these together within a single path. Let's look at an example that demonstrates how you can use the path class and different geometries within it. In this example, I've drawn two sets of shapes, two different ways. They look exactly the same. In the top cell, I'm using shapes as you would in the previous section. Here I'm using paths and geometries, which is the topic we're covering now. Let's look how the two methods differ in the markup. Here we have a canvas control, which contains a rectangle shape, an ellipse shape, and a line shape. And really nothing is different here than what you've already seen. The rectangle has a width of 200 and a height of 100. The ellipse has a height of 100 and a width of 200, and the line has the coordinates as you see here. Now let's look at the next example, which uses path elements to get the same effect. The first path, here within a canvas, has a stroke of black, stroke thickness of 2, a fill of yellow, and the same canvas.top and left that you saw in the previous example. Now, inside this path, we have a path.data element, and within that we have the rectangle geometry, which defines the yellow rectangle. Note that the stroke thickness, and fill are defined at the path, and the path.data only defines the shape itself. And the rect property indicates where this thing is. It starts at 0, 0 with width of 200 and height of 100, and 0, 0 here is relative to canvas.top and canvas.left for the path. That defines where the path starts its, well, pathiness. Down here, we have the second path. This one has a stroke of black, stroke thickness of 2, a fill of red, and again a canvas.top and canvas.left for that path. Within the path, we have our path.data element, and the data for this path consists of a single ellipse geometry with a radius x of 100, a radius y of 50, meaning a width of 200 and a height of 100, and then a center at 100, 50. So for the ellipse geometry, you specify the center point, not the upper left corner like you would with an ellipse shape. This makes it easier to animate an ellipse shape because you can move the center point around. As you'll see when you learn about animation, it's easy to animate a single point, which is all you need to animate to move this ellipse around. Finally, we have the path that defines the blue line. We have a stroke that's blue, a stroke thickness of 5, canvas.top and canvas.left for this line, and then down within the path.data, we have the line geometry element, which uses the same coordinates as the line shape did above. So you've seen two different ways to define the exact same layout. One using shapes, and the other, down below, using geometries. It seems like the geometry method requires more work, and at this point, for single shapes, it does. The power comes in combining those shapes together into a single path, and we'll look at that next. What if you need to create several different shapes that share the same fill and stroke? You can place those all within a single path using the geometry group element to combine them together. All shapes in the group share the same fill and stroke. There's no Z order defined here. All of the borders show you're defining a flat surface containing all of these elements within the geometry group. The geometry group does provide a fill rule, treating the entire group as a single drawing. Just like you saw previously using the star shape, you can use the fill rule here to treat the entire set of elements that you draw using the geometry group as a single polygon. Now, using the geometry group reduces the element count, and that optimizes your XAML slightly, because the fewer elements you have, the faster the XAML can be rendered. Let's look at an example much like our previous one, but this time we'll combine everything together into a single path. In this example, we'll look at creating three elements, that is, a rectangle, an ellipse, and a line, using paths and geometries in several different ways. Underneath all of this, there's also a text block, and I care about that because, as you can see, sometimes it may poke through the geometry that we create. But let's start with this one. This one creates three elements, the rectangle, the ellipse, and the line, using three separate path elements. Let's go look at the markup for that. First of all, we have the text block at the bottom of the stack, which contains the text. This is some text. Then we have a path, which is the rectangle. And of course, since we're creating paths individually, the Z order comes into effect in the order in which things appear. So the text block is at the bottom, then the rectangle, then the ellipse, and finally the line. So nothing's different from this example and the previous example, except that we have a text block underneath, and in this case, we're using the same fill and stroke, so I could combine these all into a single path element, which is what we'll do next. Here I'm using a geometry group to combine these together. And a geometry group takes multiple geometries and groups them together into a single shape. You can see that because all the borders display. As a matter of fact, because we have here an interior section, which by default uses the even-odd rule for defining whether or not it should be filled in, and you can see from this point here we have to cross 1, 2 lines to get out, so it's considered an even item, so it doesn't get filled in. We get some kind of odd display. But let's look at how the markup works first. In our second example, we have here a path that contains a path.data element again, but within there, a geometry group element. And that geometry group, as you can see, causes us to have far less markup. There's not individual path elements. Instead, we have the three geometries within a single path element. Within the path.data, we have a geometry group, and within the geometry group, we have our three shapes: our rectangle geometry, an ellipse geometry, and the line geometry. And by default, that looks like this. Now notice, as I mentioned, that because we have a single shape, just like that star in the previous example, there's some areas which are treated inside the object and some that are treated outside. Everything inside is filled in, everything outside is not. And because from this area, to get to the outside, you have to cross 1, 2 lines, that's even, and it doesn't get filled in. Now, if you don't want that behavior, you can, of course, modify the fill rule. If I look at the third version of this, you can see that for our geometry group, the fill rule has been set to non-zero. And by setting that to non-zero, as in the example we saw earlier, everything gets filled in now. So like I mentioned before, you only have the 2 options. You have non-zero, you have even odd, which is the default. So you just try them both till you get the behavior you want. In this case, if I wanted everything filled in, I use the non-zero rule. Here, if I use the default rule, anything underneath the shape shows through, because this is treated as a transparent region within the shape itself. In any case, if you look at the markup, you'll see how you can group together multiple shapes within a single path. Within the path.data element, add a geometry group element, and you can set the fill rule there if you like. And within that, you have the individual geometries that you'd like drawn as part of this single path. You've seen how to use the geometry classes like ellipse, rectangle, and line to create geometries that represent simple shapes. But what if you need to draw curves and specific shapes that don't fit other categories? In that case, you use the path geometry. It lets you define almost any kind of path. The path geometry can contain one or more path figure elements, and each path figure element contains information about one or more segments, lines, or curves. The path figure element has these properties: is closed, is filled, segments, and start point. Notice that the path figure defines the start point. It's not the inside content that defines it. And the is closed and is filled defines whether the path figure should be closed, that is, it closes itself from the final point you define to the first point, and is filled defines whether it should be filled or not. But it's the segments property that's most important. The segments property allows you to provide one or more segments that define a portion of this path figure. Well, what are the segment types? You can have an arc segment, that is a portion of an ellipse. You can have a Bezier segment or a poly-Bezier segment, and we'll look at creating Bezier curves, which is actually kind of complex, and you don't really want to do it by hand if you can avoid it. A poly-Bezier segment is a segment that contains multiple Bezier curves in one element. There's the quadratic Bezier segment and the polyquadratic Bezier segment, and it sounds complicated, but it's really not. Let me describe it very quickly. A Bezier segment uses 2 endpoints, a start point and an end point, and in addition to that, 2 control points that define the shape of the curve. With a quadratic Bezier segment, you have the start point and the end point, but only a single control point that defines the shape of the curve. So even though the name is longer, the curve is actually simpler. In addition, you could have a line segment or a polyline segment. It's pretty clear what that is. A line segment is a single straight line segment. A polyline segment is multiple line segments together within a single segment. Let's look at an example that demonstrates some of these features. In this example, we'll see the markup that creates this drawing. As you can see, it is a shape that contains a 5-pointed star and a rectangle around the outside. Notice that all the corners are rounded. That's nothing to do with anything except it makes it look nice. Also note that although we've asked this shape to be filled with the lawn green color, some of the areas aren't filled. These points of the star aren't filled at all. Now let's figure out why that is. If I'm on a point here and I need to get to the outside, I have to cross 1, 2 lines, and the default fill rule is even odd, and because that's an even number of lines, it's treated as outside the figure and doesn't get filled. From here, we need to cross 1, 2, 3 lines to get out, and because we cross an odd number of lines, it's treated as inside the figure and so gets filled. Now I've drawn this figure using 2 different techniques, using a line segment and a polyline segment. I could have done it all using 2 polyline segment elements, but let's look at the markup for this. Here you can see we have our path element, Stroke is red, stroke thickness is 10, fill is lawn green. The stroke line join is round, and the stroke line end cap is round. We don't have any lines, probably didn't need to set that, but it doesn't hurt anything. And down here, we have our path.data. Within our path.data, we have the path geometry element. This is the first time we've seen the path geometry element, and you can see it has attributes like, in this case, fill rule, which I've set to the default value. Didn't need to actually type that, but if you want to change it, it's nice to have it there, so you might change it to see what it does. Underneath, within that element, we have the path figure element. And you can see the path figure defines things like is closed equals true, is filled equals true, and we define a start point here. It seems weird that the path figure defines the start point, but you'll see why in just a second. Well, I'll tell you why. Each line segment inside the path figure defines only a single point. That point indicates the end point for the line. This is the start point, so we have to sort of prime the pump, as it were, to define the starting point. And the path figure does that. Here's our start point. Here's the end point for the first line. Then we draw a line from that point to this point for the second line, and so on, all the way to the final point. Notice that because I specified this is closed, we don't need to specify the starting point again for the final line. It draws the final line for us. Now that path figure defines multiple individual line segment elements. Don't have to do it that way. You could use a polyline segment, as I've done here. In this example, we have a path figure whose start point is 0, 0, upper left-hand corner, and then we define line segment starting there. So this polyline segment starts by drawing a line from the start point to here, and then from this point to this point, and from this point to this point. And for this path figure, I didn't specify it was closed, so I needed to draw a line from the next to last point back to the first point again to close the figure up. In any case, we end up with a single shape based on multiple lines, which is the rectangle around the outside of this path. Within our path, we have path.data. Path geometry obviously can contain multiple path figure elements, and each path figure contains one or more segments. In this case, we're working with line segment or polyline segment elements. Here are some things you should think about when working with lines. First of all, remember that the path describes the fill, stroke, and stroke thickness for the entire path, and it also can contain things like stroke line join and stroke end line cap, things that define the path as a whole. The path geometry contains the fill rule. The path figure maintains the start point. That's where the drawing starts. And continuous line segments could be represented as a polyline segment element, and it's probably more efficient to do things that way. What about creating arcs? An arc defines an elliptical arc, that is, a portion of an ellipse. The problem with this is there are lots of different ways to describe a portion of an ellipse, and you have to study the various properties of the arc segment element to understand how this all works. Remember, the path figure defines the start point, and the arc segment defines the end point. The x and y radius are set in the size property. So the size defines how big this arc is. There's a rotation angle property which defines the rotation for this arc. So we can define an angle of rotation that controls the behavior of the ellipse that creates the arc. And there's an is_large_arc property that defines whether we're using the large or small portion of the ellipse. You have to imagine you're drawing a portion of ellipse from one point to another. There's always two ways to do that. You could be doing the small part or the big part of the ellipse, and is_large_arc defines that. And there's a sweep direction property that determines whether you're going in a clockwise direction or a counterclockwise direction to get from the initial point to the end point. This is incredibly complicated. Let's look at our sample to see some examples of working with the arc segment element. So in this example, nothing has changed except the point. Now I've placed the point so far out that the size of the ellipse had to change as well. That defines the shape. So you can see here that by moving the point, I've changed the entire shape of this arc. Down below, I move the point once again, here to 100, 150, and in that case, I'll move this farther down. You can see that we get an ellipse shaped like this. Actually, this one does have the same size as the original ellipse did, and it's just showing a different portion of that arc. By moving the point, we've said go from this point to this point around a shape much like the original ellipse here. In the next example, we'll try changing the size and see what happens. Let's go down here. This one we start with the same reference ellipse, but for the red one, let me look at it again carefully, the size was 50, 25. If I change the size to 60, 25, you can see the red one is a little wider than the original gray ellipse. That makes sense. And on the next one, the violet one, I changed the size to be 50, 60. Originally it was 50, 25. Now it's 50, 60. In this case, the width is the same, but the height is much bigger, and we get a different shaped ellipse here. Now, I'm going to say this now, I'm going to say it often. When drawing shapes like this, you don't want to do this by experiment. You'll find it far easier to draw shapes like this using a tool that's meant for drawing shapes. Might I suggest something like Expression Blend, which we'll cover in a different portion of the course. It makes all this much easier than trying to do it here in markup. But it is important to understand what the markup is doing, and that's why we're focusing on it here. In our next example, we'll change the rotation angle. Let's go down and find that one. Here we start with the same reference ellipse, that is a start point of 25, 100, end point of 100, 100, a size of 50, 25, and a rotation angle of 0. If I change nothing but the rotation angle, here the rotation angle becomes 45, the ellipse just tilts, and we get a different portion of the ellipse that's drawn. If we change the rotation angle here to 90 degrees, it rotates it 1/4 of a circle, and now we're drawing this half of the ellipse, because that's what connects this point and this point together. Now there's no magic going on. This markup creates that drawing. So you can easily modify this markup to see the effect it has on the shapes you see in the output. In our next example, here, I'll change is large arc to see what happens. The original value, scroll all the way down to where that is here, used is large arc is true. Let's make sure I get the right one here. I need to get to the example that demonstrates this. There we go. And you can see in the original here, is large arc is true. Now down below, I have several other alterations on this. I have is large arc is false. And then in this one, I also set the sweep direction to counterclockwise. Now what difference does that make? We have two versions with is large arc is false, once with sweep direction not set, and the other with sweep direction set to counterclockwise. If we look, you can see with sweep direction set to clockwise, or not set, we just didn't set the value, we get the solid red arc from here to here. We draw it clockwise. With the sweep direction set to counterclockwise, we get the other portion, which is drawn the opposite direction from the clock. That's this, so we get the outer portion of the ellipse. In any case, try changing that sweep direction to see what happens. Actually, that's our next example. If you change the sweep direction from clockwise, or you don't define it, to counterclockwise, you'll see the default here is clockwise and we go in this direction. If you change it to counterclockwise, you'll get the ellipse drawn from this point to this point, but instead in a counterclockwise direction. In any case, you'll have to spend some time playing with the various properties of the arc element. In any case, you'll have to spend some time playing with the various properties of the arc segment element to get a feel for how the various properties change the behavior of this element. You've seen lines, you've seen arcs, now it's time for curves. Bezier curves provide the basis for just about every vector drawing program. Any kind of curve you can represent on screen can be created using a Bezier curve of one kind or another, for the most part. It makes it possible to draw just about any curve you need. Bezier curves are created using 2 endpoints and 2 control points. I will mention that the quadratic Bezier uses only 3 points and only has 1 control point, so it's a little simpler, easier to draw, easier to define, but a little less flexible. The path figure defines the start point, so your Bezier segment defines 2 control points and the end point for the line. A Bezier segment does require 4 points, a start point, an end point, and 2 control points, but the path figure that contains it, or the line segment before it, defines the start point, and all the Bezier segment element has to define is the end point and the 2 control points. Now at the starting point, the curve runs parallel to the line connecting the start point and the first control point. At the ending point, the curve runs parallel to the line that connects the end point and the second control point. In between those 2 points, the line curves. Here's a concept you may not realize. The further the control point is from the line, the greater the curvature of the line is. Now I'm going to mention you shouldn't create Bezier curves by trial and error. You want to use a tool that helps generate the XAML for you. I'll say this before, I'll say it again. Expression Blend, which we'll look at in a different part of the course, is a much better tool for generating Bezier curves. Once you generate the curve, you can copy and paste it into your markup within Visual Studio, but it's really tricky doing it by hand. Let's look at an example that shows off using Bezier curves. In this example, I've drawn 3 Bezier curves. I've drawn those curves in red. In addition, I've drawn the control points and the line connecting the end or start point to that control point in a dashed blue color. Normally you wouldn't draw those, you just draw the red curve, but I wanted to show off the relationship between the control points and the curve, so I've drawn this in this demonstration. Here we have a pretty wavy curve, here's a less wavy curve, and here we have a non-symmetric Bezier curve. Some things to point out. At the start point, the curve is parallel to the line that connects the start point and the first control point. At the end point, the curve is parallel to the line that connects the end point and the second control point. In between, the curve curves. Now that curve is defined by a very complicated mathematical function, which you're welcome to study if you like, but you don't need to. You can look at the shape and see what it does. Here we have the same behavior. We have the start point and the first control point define the shape at the beginning of the curve. At the end of the curve, the end point and the second control point define the shape of the end of the curve, and in between it gracefully curves. Here's another example that isn't symmetric. Here we have at the start point a line that the curve is parallel to connecting the start point and the first control point. And at the end of the curve, we have a line that connects the end point and the second control point that defines the shape of the curve at that point. Well, what does this markup look like? Here you can see our red path that defines the curve and the blue path that defines the lines that connect the curve to the control points. Now I will point out that I have here a path figure collection, an element you haven't seen yet. The path figure collection allows you to have multiple path figures within a path geometry and define properties that apply to the entire set of path figure elements. Here I have a path figure with a start point of 550, which matches the start point of our curve. This line segment connects that start point to the first control point. And notice in our Bezier segment element, you define the points as first control point, second control point, and endpoint of the curve. It'd be nice if the properties actually said that, but they don't. You just have to know first control point, second control point, and endpoint of the curve. Down here in our path figure for a line segment, we then create a line that connects the endpoint of the curve, here, with the second control point, here. That's how we get, in our example, the blue dashed line. And I also draw a little filled-in ellipse at the actual control point itself in the markup. In any case, the only thing that's pertinent in this example is this path figure, which contains the Bezier segment, which consists of a start point defined in the path figure, an end point defined in the Bezier segment, and the two control points, which define the behavior of each curve. Imagine a scenario where you had a lot of shapes. You'd have a lot of markup to go with it. To reduce the markup, you can use a mini markup language that describes the geometry. It's called the Geometry Mini Language, or Path Mini Language, and design tools will create this. For example, Expression Blend will create the Geometry Mini Language to define shapes that you draw on its design tools. And you need to be able to recognize and try to interpret this language if you see it. Now, you generally won't create it yourself, although you can. You'll generally see it created by other tools. It converts from this. Now, imagine we've got this shape. This is the markup you might create to create that shape. Actually, this is the markup I did create to create that shape. It had a lot of different elements defining the line segments, the polyline segment, and so on. The mini language converts that same markup to this simple markup. And as you can see, all the properties of the path are still defined. They're defined in exactly the same way. The difference is in the path.data property. Rather than having individual elements for all the various bits and pieces of this, the data property can be set to a single string which defines the entire thing. I think I can interpret this. It says move m, says move to the point 100, 0. That's our start point. Then draw a line from there to 160, 200. Draw a line from there to 0, 75. That's the L's. Draw a line from there to 200, 77. Draw a line from there to 40, 200. The Z indicates you want to end the current path figure and set is closed to true. Now, you only need this if you're going to set is closed to true. Otherwise, you could simply just move to a new point. So the Z closes off the previous one and closes it up. M moves to the point 0, 0. H200 says start at the current point, create a horizontal line to the x-coordinate of 200. Then there's the V200 says starting at the current point, create a vertical line going to the vertical coordinate of 200. Then H0 says create a horizontal line going back to the horizontal coordinate of 0. And the last V0 says starting at the current point, make a line that goes to the vertical coordinate of 0. And that draws the box around the outside. Now, I didn't create this. What I did was take the markup in the upper box, copy and paste it into Expression Blend, make some change or another which causes Blend to recreate the markup, and this is the markup it created for me. That mini language can be very helpful for you in optimizing your markup. That's why Expression Blend uses it. Now, I would recommend that you don't try to create your applications using this mini language because it's completely unreadable for the most part. You have to stop and interpret every bit of it yourself. You have to create your own mental mini language interpreter. To work around this, create your markup any way you like, and then let the tool generate that mini language for you. Now, this is all documented. You can go to this URL on Microsoft's site to get more information about the Geometry Mini Language. My only point is that you should learn that it exists, and you need to learn to recognize it in your code when using a tool that generates that mini language. You've seen an example. Now go play with your own and try out using the Geometry Mini Language to optimize your markup.